Good morning, everyone, and thanks for coming along to another Earth Institute Coffee Morning. Where this morning, Lennon, who's from the same school as myself, it's great to see another person from the School of Maths giving a talk to the Earth Institute. We'll be talking about soil modelling and how that impacts on a slightly wider scale. We were chatting a bit because we both worked a bit with Teagasc and with Med Éireann, so I'm really interested to see what his involvement is with them. But he says it's going to start off really small and see how it connects to the bigger city.
Yeah.
Thank you.
Thank you, Connor, for the introduction, and thank you, Will, for the invite and for when you set up. And so I was told to keep it light, so I have only 10 slides, and each slide has 10 equations. Only joking. So no, I am keeping it light. So there's a whimsical title: How the Earth Institute Helps Some Mathematicians to Fall in Love with Soil. And it echoes a talk in the same series that my collaborator, Saoirse Tracy, had a while back, picking up the same theme. And this is a joint project with Saoirse and Graham Benham, who is also here. Graham is from the School of Mathematics and Statistics, same as myself.
Right, that's fine. Okay, perfect. Thanks, Katrina. So just a little bit of history, the history of this project, if you like. It all started back in 2021 when the Earth Institute organized a networking event. And I just highlighted the date here, March 2021. I think we were still in some kind of lockdown and the event was on Zoom. And it was Katrina who organized it. And the aim of the event was to connect researchers in maths, statistics, and computer science with people working in sustainability and environmental research. So I just presented the stuff I was interested in, and Saoirse Tracy was at the event as well, and she said, "This sounds, interesting. It's similar to some of the things I've been doing. So why don't we try to get a collaboration going?" And it's very easy after these events to have, big ideas, but then you realize, well, how do I actually get a collaboration up and running? It takes time and more importantly, it takes money. We started very small. So after this workshop, the Earth Institute organized a seed funding competition, and you could put in an application for the seed funding, and it had to be a joint application with somebody else from the event. So we put in an application, and our aim in our proposal was to develop a data-driven mathematical model of soil compaction. So you might as well start very ambitious. And we had some objectives. We wanted to formulate a computational model of soil compaction using this open foam software, it's called. And then we were going to configure the model using data from the X-ray CT scanning facility here in UCD over in Rosemount. And then we were going to implement the model on iCheck, the Irish Centre for High-End Computing. So that was very, very lofty aims for a project that had 750 euros worth of funding, I might say. But we were successful. So back in May 2021, we got the good news that our seed funding application was successful. And I got the email from Katrina, and she said she was pleased to let me know that the panel decided to make 3 awards, and our application was successful. I later found out there were 3 applications. Anyway, that's a great, but that's maybe that's facetious, but it's good in a way. We're so used to applying for funding where the success rate is 5% or 10%. So here's one where it's 100%. The amounts are small, but it helps to get you going. So it's one of the benefits of being in the Earth Institute, or even just affiliated with it. So anyway, the idea that we had here was this mathematical model of soil compaction. So water draining through the soil, it's obviously a fluid, and it can be modeled with the equations of fluid mechanics, which are the Navier-Stokes equations. And I don't have to explain those here because they were already well explained in a previous talk in this series by my colleague, Miguel Bustamante. So we have these equations anyway that describe the flow of a fluid in a domain, or a container. And the domain in our case is the soil. And the soil is actually a porous medium. You know, so it provides I should say the pore structure provides the domain or the geometry for the problem, and we have some natural boundary conditions then. So we have our mathematical model. And then the idea that we had back in 2021 was, yes, that we would obtain this geometry from scanning a soil core sample, and we would then convert this geometry or this domain into a digital representation, basically an STL file, and you can then feed that into your Navier-Stokes solver, and you then solve and you describe how the flow of the water through the soil, how it goes over time. And then the idea is that, you know, different levels of soil compaction and also different types of soil lead to different porous medium structures, therefore different flow geometries and then different flows. So, you know, that was the ambition. You kind of aim for the stars, and then like the motto of UCD, aim for the stars and then maybe you'll hit the top of the trees. So what we ended up doing with the small amount of funding, we were able to supplement it with some, you know, bits and pieces from research accounts, and we were able to get some summer project students and master students working on toy problems. So this is a lovely simulation that some, you know, final year projects and master's projects did, or project students did, where they kind of this is not a soil core. It's a kind of synthetic, kind of made up geometry, but it's a porous medium. So it's the type of thing that, you know, we should be simulating, and then they just you know, set up a computational model where you're describing the drainage of the fluid through the porous medium. So I should say this is a toy model, a toy geometry, but it shows that this kind of approach works. It's a proof of concept. And here we've used the OpenFOAM CFD software. So this is a great piece of software for all your simulations based on the Navier-Stokes equations. You don't need to hand code the solutions of the Navier-Stokes equations. You feed in your geometry file, you generate a mesh, you specify your boundary conditions and your initial conditions, and you let the simulation run. Now, it's never as easy as that, of course, because, you know, when we're doing science, we want to check our results are robust. So you need to make sure that your simulations are robust. For example, making sure you have enough mesh points in your simulation, and so on. But it establishes that we're on the right track if we want to do this kind of thing properly. So after that, we got a bit maybe despondent because you know, after all this effort with all of the students, we had solved a toy problem, if you like. We were just simulating the flow of water through a synthetic porous medium geometry. We weren't anywhere close to the real thing. We realized that these toy models, or going beyond the toy models, requires a lot of resources, a lot of inputs. You need a lot of dedicated time and effort. When you're working on these simulations, there's a lot of debugging. Sometimes things work on a laptop, and then you want to upscale the simulation and do it on a high-end computer. And, you know, getting the equivalent piece of software to work on the high-end computer can be months. You know, just figuring out how these things work. And then there's the data visualization in 3 dimensions, and then validation. Like, these are just simulations, and there's not a very clear connection to the real world yet. So, you know, what were we doing really? And then we kind of felt we needed a focus for our work, that we wouldn't just be doing colorful fluid dynamics. So solving the Navier-Stokes equations on a computer, that's called computational fluid dynamics, or CFD. And if you put CFD into Google Images, you see all these beautiful images of, you know, vortices and mixing in the atmosphere, or you know, turbulent jets, vorticity streaming out of a jet engine, all these things. And the detractors say this is just colorful fluid dynamics. You know, what are we doing science or animation? So we kind of felt we needed a focus for all our work. And then this thing kind of cropped up then. We got invited to this planning meeting for VistaMilk. This was in November 2021. VistaMilk is an SFI funded consortium, and it has this very high level ambition to digitalize the dairy industry. So putting sensors on cows, putting sensors in fields, breeding, genomics, trying to optimize milk production. That was the aim of VistaMilk phase 1. Phase 1 has just finished, and phase 2 is starting. And so we got invited to participate in phase 2. And it was very interesting being in the room when people were mapping out what phase 2 should achieve. And there was a real understanding by a lot of the researchers and a lot of the, you know, the international scientific committee that it shouldn't just be about, you know, optimizing the dairy industry. It shouldn't just be about profit. It should be about sustainability as well, and doing more with less. So some of our research will have that sustainability focus. So it was really nice to hear that, you know, the dairy industry is aware of these issues. So yeah, we got invited then, based on our preliminary work, to participate in phase 2, the System of Systems platform. And that was the beginning of our soil modeling group. So that's where we came together and had a bit more of a focus. So that's Saoirse in the School of Agriculture and Food Science, myself, and then Graham Benham, who came in on the project. And we have 2 very clear targets for what we're going to achieve in VistaMilk 2. We want to develop a new model of the soil moisture deficit, which, yeah, a new model. And this is going to feed into an already existing grass growth model that Teagasc has, and also that Met Éireann uses. So Met Éireann publishes a grass growth forecast, and sometimes it'll even be on the news. So Teagasc want to improve the accuracy of that forecast, and that's where we're going to come in with our soil moisture deficit model. And then on a more fundamental level, and going back to the idea we had in the seed funding project, we're going to develop new drainage curves using our CFD and the X-ray CT scanning. And those will then be used to better inform the soil moisture deficit model, which we're also going to develop. Just wondering, how am I for time? Okay. So I might show just one or 2 equations then. Are you? Should I ask again? How am I for time? So anyway, the first aim we have is the soil moisture deficit model. So in the current grass growth model, you know, we'd call this a difference equation, or it's a mass balance equation, that the soil moisture deficit on day T is the soil moisture deficit on the previous day, minus the rain plus the evapotranspiration plus the drainage. And I've just been talking to the modelers in Teagasc, and they say the thing that they're not happy with, or that maybe that's not fair. The thing that they see could do with some improvement is the drainage model. So I looked at this kind of difference equation, and I realized it's actually a PDE in disguise. PDE is a partial differential equation. And this is when the applied mathematicians start to get interested in a topic. So maybe falling in love is a bit of an exaggeration, but this is where we get interested. So the soil moisture deficit, it's actually a PDE in disguise. Theta is the soil moisture content, and then K the hydraulic conductivity, and psi is the capillary pressure. And there are models for these particular things, and these models are called drainage curves. So if you like the model inputs, if you want to make a prediction, you need your inputs first. The model inputs are the daily rainfall and the evapotranspiration, and then also your drainage curves. So this PD is called the Richards equation, and it turns out it's very challenging to solve this numerically. It's a whole world of people working on solving this equation. And I say when a PDE has some issues like this that makes it hard to get a solution, that's when the mathematicians get very interested. So what we're thinking of doing for VistaMilk, because we want an operational forecast, we don't want to be solving a stiff PDE that takes forever to generate solutions. We're looking at kind of doing a depth average version or a 2-layer version. And we hope to couple that to the existing Teagasc grass growth model to give an improved prediction for the drainage rate. So then just the second thing that we're hoping to achieve, this second aim, it gives a bit more structure to the early efforts that we had when we produced the toy models. So here really we're going to go for it. We're going to X-ray CT scan the soil core samples, generate the STL file. So it's this kind of thing here that describes digitally the porous medium structure. And then we're going to use that as our flow domain for a simulation using open foam. And then the result, so now we have the focus. What is this going to do? It's not just colorful fluid dynamics. We're going to be able to post-process these results, and that will give us data to generate more accurate drainage curves. So that's really it. So the summary, just to thank the organizers and the Earth Institute for giving me this opportunity and these opportunities over the years. It's been an excellent way to link up with researchers in very different areas. And the take-home message is, the small amounts of funding, they can lead to much bigger things down the line. But I would say that, patience is required. It's a long game. So I started in March 2021. And then the seed funding was November 21. VistaMilk 2 is due to be launched officially next week, I think, in the Mansion House. And then, the timeline there is you're thinking 4 years, 3 or 4 years, if a PhD student is working on this. So the soil moisture deficit model, the updated one that we hope to develop, we're thinking maybe it'll be operational 2027. So really it's 6 or 7 years to bring a project to fruition. It is a long game, but it's enjoyable. So thank you, Will, and thanks